Hello, this is Alex Yazdani. This is a demo for Lab 9 of EE533 with Professor Young Cho in the spring of 2025. My lab partners are Szymon Gorski and Tim Liu. So in this lab, we needed to convert our pipeline processor that we've implemented on an FPGA into a multi-threaded processor to run 4 threads. This is useful so that we actually don't have to detect and prevent hazards. And for pretty much most real applications, you're going to be using multiple threads anyways, so it makes sense to do this. And first, I'll just start by downloading the bit file onto the FPGA and getting that set up. So and we've gone ahead and created a new Perl script to load everything. So we have 4 separate iMemories that we can load. So the command is to load IM1, and then we'll start with just, we have a checksum program, which you can read more about in our report, but it essentially just loads in 5 different values, and for each thread, it reads in 5 different values and then just XORs them all together and writes that back to memory. And so there we just loaded one of them. And then here's for the second thread. And then here's the third thread. And then the 4th thread. And then we still only have 1 data memory, so we can just load the data file into data memory. And so now if we we can dump data memory. So right now I only have it set up to read the first 40 addresses, but for this program we're using, I think, the first 24 addresses. So basically each thread just reads in 5 of these values, XORs them all together, and then writes to the next one. So we haven't run it yet, so these values are still 0. But also we can dump the register file, and again, right now, since we haven't run the program yet, everything should be 0. But if we just do run and then stop, that basically enables the entire pipeline and then disables it again. So now if we dump data memory, we can see here, I think this is the correct checksum. I know just because I've seen it a bunch of times already. Same with this. And then I believe this is the next one. And then, yeah, this is the final one. And so you can verify that just by looking and actually XORing these, or you can refer to our report to verify that that's correct. And then if we dump the register file, we can see the values that were loaded in, the values that was written back out after XORing, and then this is basically just our iterating variable. So we can also go ahead and do a reset right here, and then we're also able to get sort working, so the bubble sort that we used in a previous lab. So I have 4 different sort programs. The only difference between them is they have a different base address. So they're all doing the exact same thing. They're just working on different variables, but I'll load all 4 of them into the respective IMEMs. And then we just need to load, I think it's data 4. So now if we dump data memory, so we can see the first 40 addresses. Just look at them in increments of 10 basically. So each thread will work on 10 of these. And yeah, we've just, each one is the same, but our threads should be able to sort each 10 of these individually. So you can see they're all unsorted right now. Then if I just do run and then stop and then we'll dump data memory again. So now you can see each group of 10 has been sorted in an incrementing way. So 0 up to 9. And yeah, so we have this checksum algorithm and the bubble sort working on our multi-threaded processor for 4 threads. So now I'll pass it over to Simon, and he'll just kind of go through some of the background of our design and the software programs as well. Thank you.
Hello, my name is Simon. My lab partners are Alex and Tim. I'll be reviewing the C side and assembly of our project. First of all, we have our checksum program, which is our objective is to use a networking C file. So this is what we came up with. And there are 4 different versions of this that each have different hex values for the payload. So that will return a different checksum for each program. And it's just a simple assembly to do that. Each program would have a different base pointer, because the DMEM layout is as shown here. So thread 1 would access this half and have its checksum be printed here. Thread 1, 2, and 3, like so. And these are the expected values that we should see in our DMEM once this is all done. And here is our pipeline. So the additions we've added are muxes to 4 PCs now instead of 1, and 4 IMEMs instead of 1 IMEM. And each of those are muxed all around to update the PC if there's a branch or just incrementing. And we use a thread counter in the IF stage, which gets carried along the pipeline for each instruction. And it gets used, for example, in the mux that goes to the reg file, which we have 4 reg files now. And there are 2 muxes, one for the read addressing and one for the write backstage. There's a mux for the output. And again, the thread ID is being carried along the whole path. And we had to have 4 NCCV flag registers, one for each thread, which get updated based on the mux as well, of the thread ID during the execution stage.